Hello, my name is Ethan Lego, and this is my project 2 for fluid mechanics. And this is the video portion for that project. As you can see, here's my already created system. And now I'm going to create a second one to show you how I did the first one. I'm going to call this 2D airflow flat plate example. I'm going to click geometry, make sure that I'm in 2D, and I'll select Design Modeler. All right, so now that I'm in Modeler, I'm going to first put on a grid, and I'm going to make this grid pretty small. All right, let me zoom in here. Okay, so I'm going to grab a rectangle, and from the origin, I'll drag out. I will add dimensions. All right. And for my length, I'm gonna do 1 meter. And for my height, I'm gonna do 0.05 meters, which falls within the recommended 2 to 4 times the boundary layer thickness. Um, and then I'm going to go to concept, surface from sketch. Let's get rid of this. I'll do box select, and I'm going to select those, click yes, and click generate. And now we have our surface. Now I can go back to my workbench, click mesh, and edit. All right, so now that I am in mesh, I'm going to, first I'm going to name all of my edges. This is going to be the upper boundary. This is going to be our plate. On the left, we have our inlets. And to the right, of course, we have our outlets. All right, so now that I've named those, I'm going to click Mesh, Insert, and Sizing. I'm going to select the upper boundary and the plate, Apply. I'm going to use 1,000 divisions. I'm going to turn off Capture Curvature, make sure my behavior is hard, and click Generate. All right, so that mesh has been created. Now I'm going to do the same thing. And I'm going to select my left side, hit apply. I'm going to make sure my number of divisions is set to 100 with the sides. Turn off capture curvature. Make sure my behavior is hard, but this time I'm going to use a bias. And I'm going to use a bias factor of 5. And now I'm just going to zoom in to make sure that that bias looks correct. And yes, it does. and I'm going to click generate. All right, so now that that left side mesh is done, I'm going to do the right side. Go over to the right side. And I'm going to click this edge, apply, number of divisions, 100, turn off capture curvature, hard, and I'm going to do a bias factor of 5. And this time I'm going to reverse the bias, and it should now look correct. Yep. And I'll click generate. All right, so now that that mesh is done, I'm going to go finally to insert face mesh. I'm going to select this face, hit apply, and click generate. All right, that face mesh has finished off. So now I have this nice looking mesh with a slight bias towards the bottom where all of the boundary layer is. All right, so that's the end of the meshing. And I'm going to go here and click update. And that is updated. Now I'm going to go to setup. Now that I'm in setup, I'll choose double precision and 4 processors. And now I'm going to let that load. All right, now that my mesh has loaded in, I'm going to change the model from viscous, whatever this is, to laminar. I'll go to materials, fluids, air, and I'm going to change the density to 1.2 and the viscosity to 1.8 as per the project directions. And I'll click close. And now I'm going to go over to boundary conditions. For the inlet, I'm going to make sure that my velocity magnitude is 2 meters per second. For the outlet, I'm going to make sure that prevent reversed flow is on. For the plate, I'm going to make sure that it's stationary, and it is. And then for the upper boundary, I'm going to actually change the upper boundary to symmetry instead of a wall. So that the CFD understands that it's not a physical wall, it's just a computational wall. I'm going to go to reference values. And I'm going to make sure I compute from the inlet. And here I have all of my reference values, making sure that they all look correct, and they do. The reference zone, I'm going to select surface body. And then I'm going to initialize. All right, now that that initialization is done, I'm going to click Run Calculation. I'm going to select 500 iterations, and I'm going to click Calculate. This should be 500. All right, now that my calculations are complete, I am going to go back to my workbench and I'll edit my results. All right, now that I'm loaded in, I'm going to select line and I'm going to put in a few different lines here. The first one is going to be the midpoint, and there we are, 100 samples, and it looks good. I'm going to do the endpoint, and here I'm going to do 4.999. Sorry, just 9, 0.999. Once again, 100 samples. That looks good. I'll do the same thing for the near the inlet. Roughly 5 centimeters from the inlet. And then I'll do the exact same for um, X at 35 centimeters. And finally at 75 centimeters. Got that. Okay. And so now I'm going to create a contour. First, I'm going to do velocity. Oh, velocity contour. I'm going to select velocity U. I'm going to do 100 contours and click apply. Oh, I see. Okay. Here, make sure I'm selecting symmetry 1, clicking apply, and there we go. You can see the boundary layer at the very bottom getting slightly bigger as it goes along the plate until it reaches the end. I'm going to add another contour. And this is going to be a pressure contour. And so here it's going to be symmetry 1, variable pressure, and I'm going to use 100 contours as well. And there you can see if I just turn off velocity contour, you've got this very front heavy um, contour over here. And now I'm going to add in my velocity vector. I'm going to do this at the endpoint so it's visible. I'm going to use a constant color, black. I'll use arrowhead or arrow 3D, and I'm gonna make this a 0.09 size. Click apply. And if you look very closely over here, we have our velocity vectors. And now I'm going to do the same thing, but I'll just put those velocity vectors everywhere. And so I'm going to select symmetry 1 instead of endpoint. Make it constant. And this time I'm going to use a line arrow, and I'm going to do 0.02 for its size. And if I take away the velocity contour, you'll be able to see very small little arrows that taper off at the end. And this shows how in the boundary layer, the velocity is very different. I'm going to edit my legend. I'm going to make sure that it's horizontal. I'm going to increase the size to 1, and I'll use fixed notation. And so now if I turn off my velocity vector for the entire plate, I'll turn on my velocity contour. And here we have our corrected legend. Now I'm gonna open up a new chart, and I'm gonna name it velocity profile. The title is gonna be airflow across flat plate velocity. I'm going to select my data series. My first one is going to be the outlet is endpoint, midpoint, which is at the midpoint at x equals 35 centimeters, the x 35, x equals 75 centimeters, which will be x 75, and finally near the inlets, which actually is at x equals 5 centimeters. Right, for the x-axis, I'm going to do velocity. For the y-axis, I'm going to use y. All right, so now you can see all the velocity profiles here. They're all roughly ending at 2. and they all peak around 0.01 meters. That's what the boundary layer thickness should be. All right, and the last thing I'm going to do is for the wall shear stress, the skin friction, the coefficient skin friction, and I'm also going to look at the coefficient of drag. So to do that, I'm back here in the CFD base. I'm going to go to plots, select XY plots. I'm going to select wall flexes, wall shear stress on the plate. I'm going to plot that just to make sure that it looks correct, and it does. I'll write to file. I'll just call this CF sample, and I'll store it in documents. And then I'm going to also do the same thing for skin friction coefficient. I'll plot that, make sure it looks correct. This is going to be skin friction example. All right, I've exported both of those. And so now I'm going to go over to Excel. All right, so I have my two data sets here in Excel open. I'm going to open this data set, and I'll open it with Notepad. And so here you can see all of the data. I'll just copy everything and place it in my sheet. And I'll do the same thing for, oh, I'll do the same thing for the skin friction. All right, so I have both of them here in Excel, and I do believe, yeah. So when exporting and bringing it into Excel, there are some issues with the data points and how they are um, printed out. So I'm going to go and fix those right now, and I'll come back. All right, so now that I'm back, as you can see, I fixed those values and how they were printed in order. Um, and so we've got the wall shear stress versus X and our skin friction versus X. And after putting them through creating a charts, we have our tau, and we have, no, I'm sorry. This one is the tau, and this one is the skin friction. And then finally, to get our drag, we use our formula, and I grabbed um, the last Reynolds number coefficient that I also exported into Excel right here at the end of the plate, and we got that value. And that's it.